let's see an example where this is used. So we have already computed the Laplace transform of sin t, which was 1 over s squared plus 1, and this is defined in the region s greater than 0. So now the question is, what is the Laplace transform of sin omega t for some omega, a positive real number? So we have seen that the Laplace transform of f of lambda t is 1 over lambda f of s over lambda, and we can simply plug in lambda to be omega and small f to be the sine function. So for f t to be the sine function and lambda is omega, we get the Laplace transform of sine of omega t is equal to 1 over omega f of s over omega, but here f is simply this function 1 over s square plus 1. So this is 1 over omega 1 over s square by omega square plus 1, and this is defined for s greater than 0 again, because omega times 0 is just 0. So in the end you get 1 over omega square by s square plus 1, and 1 omega cancels out, so you get omega by, sorry, not 1, omega square, omega over omega s square plus omega square for s greater than 0. Similarly, one can compute the Laplace transform of cos omega t, and this is just s by s squared plus omega squared, and the region of convergence is again s greater than 0. Okay. Now as a sanity check, we try to compute the Laplace transform of e to the power alpha t for some alpha positive. Then we know that the Laplace transform of e to the power t is given by 1 over s minus 1 for s greater than 1, right? So in terms of our change of scale formula, the Laplace transform of e to the alpha t should be 1 over alpha times 1 over s by alpha minus 1. So this is just f of s by alpha, where f s is 1 over s minus 1, and this is just 1 over s minus alpha, and the region of convergence is s greater than alpha times 1, this is alpha. So you get the Laplace transform of e to the alpha t is 1 over s minus alpha, s greater than alpha, and this is exactly what we got from a direct computation. So this formula is okay. Now let's try to compute an example using both linearity as well as change of scale formula. So let me write ft is 3 exponential 2t plus cos 5t for t greater than or equal to 0. So what is the Laplace transform of ft? This is simply the Laplace transform of 3 e to the power 2t plus Laplace transform of cos of 5t, and here you can of course take the 3 outside the Laplace transform. So 3 times Laplace transform of e to the power 2t plus Laplace transform of cos 5t. So let's see what it is. So the first one is given by, so of course all these are variables, functions of variable s. So the first one is simply 3 over s minus 2, and the second one is given by s squared plus 25, and the region of convergence is the intersection of the two regions of convergence, which is here simply s greater than 2, because this one is defined for s greater than 0 and this one is defined for s greater than 2. So the intersection is simply s greater than 2. Now we can try to evaluate it, but it's not important. So you can try to write it in this form, plus s minus 2 by s minus 2 times s squared plus 25, s greater than 2, and here one gets 4s squared plus 75 minus 2s over s minus 2 times s squared plus 25. So for this region s greater than 2. So we have seen that in this case, in the first line we have used linearity, as well as for the second term we have used change of scale, and as well as for the first one also change of scale. Change of scale. So we see that using linearity and change of scale we can evaluate the Laplace transform of sums of functions as well as functions which are defined by changing the scale of the domain by some positive constant. Now let us come to the properties that I mentioned before, which is the first and second shifting properties. So first let's look at the first shifting property. And this says that given that the Laplace transform of a function ft is fs for s greater than alpha, then for a constant c, the Laplace transform of the function exponential ct ft. So we are just multiplying this function ft by exponential of ct, and this is given by f of s minus c, and the region of convergence should be s greater than alpha plus c. So this is very easy to prove. So we can simply write out the definition of the Laplace transform and it will follow from there. This is integral 0 to infinity ft exponential ct exponential minus st dt, and this is simply ft exponential minus s minus ct dt, and this is nothing but the Laplace transform of the function small ft evaluated at the point s minus c. So the only thing now remains is to compute the region of convergence, but we need s minus c to be greater than alpha because our initial function fs is defined for s greater than alpha. So since now we have the argument s minus alpha, it should be s minus alpha should be greater than alpha, but this is nothing but s greater than alpha plus c. So we have seen that the Laplace transform, when you shift when we multiply by an exponential function with constant c, then the Laplace transform on the right hand side gets shifted by c horizontally. This is why it's called the first shifting property. A second shifting property is given as follows. So suppose again that the Laplace transform of ft is given by fs for s greater than alpha. Now define a new function gt to be f of t minus a for t greater than a and 0 for t between 0 and a. So a here is a positive constant. So now we have shifted the whole function f of t to the right by defining this function gt to be f of t minus a for t greater than a. So this means that when t approaches a, then gt approaches f of 0. So our domain gets shifted to the right, and this is why it's called again the shifting property. So we have defined this new function gt. So the second shifting property says that the Laplace transform of gt is given by exponential minus as capital Fs. So we see that from the first shifting property, multiplication is by exponential ct on the left of the Laplace transform, but in the second shifting property the multiplication is by exponential minus as on the right hand side of the Laplace transform. So let us again try to prove this second shifting property. So I want to show that the Laplace transform of gt is exponential minus as times fs. So we can simply write out the definition of the Laplace transform of gt, but we can now break this integral, which is from 0 to infinity, in two regions, from 0 to a gt exponential minus st dt plus a to infinity gt exponential minus st dt. Now in this region 0 to a, this gt is simply 0. This is by definition. For t in between 0 and a, this is simply 0. So we are only left with the second integral. So let's see what is our second integral. So it's 0 a to infinity gt exponential minus st dt, and this is given by a to infinity f of t minus a exponential minus st dt. So again now we can make a change of variables. U equals t minus a, which means that du equals dt, since a is a constant. And let's see what are the limits of integration. When t equal to a, this means that u equal to 0, and when t equal to infinity, this means that u equal to infinity. So we can write this integral after the change of variables. So this is the change of variables. So now we can write this integral as 0 to infinity f of u exponential minus s times u plus a dt, but note that this is equal to 0 to infinity fu exponential minus as times exponential minus su du, and now you can simply take this outside the integral. So I can just delete it from here and you can write it outside the integral, and what we are left with inside the integral is simply the Laplace transform of f. Therefore, as in the end we get as answer the Laplace transform of gt is simply exponential minus as fs. Now note that if fs is defined over s to s greater than alpha, in this region s greater than alpha, then the Laplace transform e to the minus as fs is also defined for s greater than alpha. So the region of convergence will not change because exponential function is defined everywhere. So the region of convergence will only depend on the region of convergence of this function f, which is s greater than alpha. So let's see another example where we can use the shifting property. So let's compute the Laplace transform of e to the power ct cos theta t, where c and theta are constants, real constants. So we are assuming both to be greater than 0. So by the first shifting property, this is nothing but the Laplace transform of cos of theta t applied at the point s minus c, and this is defined for s greater than c. So note that here we have taken our function cos of theta t to be our ft, and so we are trying to compute the Laplace transform of e to the ct ft, which by the first shifting theorem is f of s minus c, where f is the Laplace transform of ft. But here we know what is the Laplace transform of cos of theta t, which is nothing but s minus c. Note that we are evaluating at s minus c, so wherever there is an s, we replace it by s minus c. So since the Laplace transform of cos theta t is given by s squared plus theta square for s greater than 0, so when we replace s by s minus c, we get s minus c by s minus c square plus theta squared, and here s is again greater than 0. So in fact we don't need it to be greater than c, this is well defined on the region s greater than 0. So in this way we can apply the first shifting theorem to compute the Laplace transform of any function which is multiplied by e to the power ct in the input function. For the second shifting property, let's see another example. So let's say our ft is given by cos of t minus pi by 3, t greater than equal to pi by 3, and 0 if t is between 0 and pi by 3. So in this case, this is simply the way we define the shift gt from ft. So here our ft, so let me write this as gt so that no confusion occurs. So this new function is defined using the cos function, which is f of t, and we define this new function gt using the shifting in the domain. So the Laplace transform of gt is by the second shifting theorem. This is the second shifting theorem or second shifting property, should be given by the Laplace transform of cos t evaluated at s, and you have to multiply by e to the power minus pi by 3 times t. So this is the A in the second shifting property. This is A, and we know what is the Laplace transform of cos of t. So in the end, this should be S. So in the end we get minus pi by 3 times S over S square plus 1, and here the region of convergence is simply S greater than 0. So we have applied the second shifting property for this example. In the next lectures we will continue to develop more properties of the Laplace transform, which will help us compute the Laplace transform of more and more functions.